Moving on, the last talk in our coal session is by Cortland Eble. Cortland is an organic petrologist, coal geologist, worked at the survey for over 25 years on coal and more recently organic shales. And he's going to talk about a potential new use of coal and coal byproducts in the area of rare earth elements. So, Cortland.
Thank you, Dave. His introduction is a nice way of saying I'm kind of a nut. Today I'm going to talk to you about some research that we're doing here at the KGS and the University of Kentucky, across the entire school, about these things called rare earth elements and how we may be able to extract them to be an economic resource. That's the title of my talk is there. Back in last year, 2015, we applied for and were awarded a grant from the United States Department of Energy. And up there you see that is the official title of the project, pilot scale testing of an integrated circuit for the extraction of rare earth minerals, etc. It is funded by the U.S. Department of Energy and National Energy Technology Laboratory. It's in an area, there were two areas of interest. Ours fell into area of interest 2. And it is indeed the University of Kentucky, which includes the Department of Mining Engineering, the Kentucky Geological Survey, and the Center for Applied Energy Resources. And our principal investigator is Rick Honecker, who is the chair, head of our mining engineering department. And the total award from DOE was $1.3 million. The project objectives are as follows. We want to develop, design, and demonstrate a pilot-scale processing system for the efficient, low-cost, and environmentally benign recovery of rare earth elements from coal and coal byproducts. Coal byproducts would include material that is being so-called waste material from coal preparation facilities, and we're also looking at the ash byproduct from coal-fired generation. The pilot scale circuit will have a dry solid feed rate of about 1/4 ton per hour and will be capable of producing about 5 to 7 pounds of combined concentrates of REEs with purity levels of about 2%. And I'll ask you to hold on to that 2% because that's 2% is 20,000 ppm. It's what generally is regarded as ore grade material. And I'll show you in some subsequent slides the challenge that's facing us to get to that level. We will both technically and economically test the feasibility of the system, and with respect to the separation performance and operating costs and, of course, environmental acceptability. Here's our team. There are other people here that are involved, the worker bees actually, but up at the top we have Rick, who is the head of the project. 2 people, Jack Brocco and Jim Howard, who are at our Center for Applied Energy Research next door, and myself at the bottom here. But there are others, many others involved in this. First of all, this is not going to be a very technical talk, but what are rare earth elements? Very simply, they are the lanthanide series elements, shown here, and usually you will see the term REE plus Y. Y being yttrium, Y yttrium. It's technically not a lanthanide series element. The reason is that it tends to occur with lanthanides. It behaves like an anthanide, or lanthanide, and therefore, and it does have some uses that go along with the lanthanides. Another thing is that you will see that these are, the numbers at the bottom are atomic weights, and right around europium here, EU. From here down, those are regarded as light REEs, and the ones up to lutetium are regarded as heavies. And down here are the actual names of the elements, which with a little practice you can pronounce them without hurting yourself. Another thing, rare earth elements, the name, is really a misnomer. The persistence of the term, it reflects unfamiliarity with it rather than true rarity. Several REs have crustal concentrations similar to many base metals, which would include chromium, nickel, copper, zinc, and others. Oddly enough, REs with even atomic numbers are more abundant in the crust than ones with odd numbers. I have no explanation for that, but that's just the way it is. On the chart here, you can see where I've circled where the rare earth elements occur in terms of abundance. So you can see many other base metals falling into about the same level. Our rarest metals, which would include gold down at the bottom, truly are less abundant than these rare earth elements. Now, just a brief run-through of where we have gotten REEs historically in the United States and where we are now. Back in 1949, a carbonatite intrusion with high REEs was discovered at a place called Mountain Pass, which is in the Upper Mojave Desert in California. That was taken over by a company called Molycorp, to which they then started mining and processing material and quickly became a major source of REEs. Ironically, the early development was supported largely by the introduction of color television sets. I'm old enough where I can still remember the advent of color televisions and all the excitement that came with it to watch cartoons in color on Saturday morning. From the mid-60s through the mid-80s, Mountain Pass became a dominant source of REEs. And with just that one mine, the United States was largely self-sufficient. But that was before PCs and cell phones. They hadn't arrived yet. And again, I'm old enough to, I remember the times when we didn't have these. Starting in about 1985, large discoveries of deposits in China were found. And the Chinese quickly increased their production dramatically and literally flooded the market with low-cost REEs. At about the same time, the production from Mountain Pass started declining rather significantly through a combination of environmental, regulatory, and economic pressures. It was kind of a triple whammy for Mountain Pass, to the point where for right around 2000 it did shut down, it closed its operations. So starting in about 2000, all of the REEs used in the United States come from China. One, because they were economically it made sense to do that. And what this chart shows is just okay, here would be our initial phase of the mining. It's taken over by Molycorp here, starts ramping up till about 1985, where we really were self-sufficient, and then from about 1985 on, it's referred to as the Chinese era, where not only the United States, but just about every other country in the world is getting their REE supply from Chinese material. And that, on the one hand, economically, it made a lot of sense, but from a strategic standpoint, it really made a lot of people very nervous, because a lot of these REEs, as I will show, they're very critical in many, many things we take for granted today. Everybody in this room, I think, has a cell phone. It relies on REEs to work. Everybody has a personal computer. Again, REEs. From a military standpoint, it's even more critical. So what we needed in this country is, where are we going to get future REE supplies? Well, Molycorp started opening again in the early 2000s until about the big drop-off in about 2012, 13. And what you see here are the prices. Mountain Pass was predominantly producing REEs that were classified as light REEs. And one thing that to keep in mind about these elements is that they have different values. And typically, the light REEs don't command as high a price as the heavies. So when this price really went down, really plummeted, it's something. And in June of 2015, they declared bankruptcy. The heavies suffered a similar fate, but you can see the price that you're getting for the heavies far exceeds that of the lights. So countries like China, which are dominantly heavy REE suppliers, really weathered that storm much more capably than Molycorp did. Some applications. Magnets. The REEs are used to produce very small, lightweight, high-strength magnets that allows things to be miniaturized. Okay, if you think of your cell phone, that's a good example. Portable disk drives, DVD drives. All of these things would not be possible without REEs. Refrigeration. One thing that is still coming on, but it's coming on strongly, is magnetic refrigeration. And this is, again, through the use of rare earth elements. It's far more efficient than gas compression refrigeration, which uses Freon. It does not require any refrigerants that are flammable, toxic, have the capability of depleting the Earth's ozone layer, and possibly contribute to global warming. So from an environmental standpoint, it's much better than gas compression. Two elements, one I mentioned before, europium, critical in any kind of color monitor or television set. And then another one, erbium. We talk about fiber optic communications. Erbium is critical to these because what it does is they lace some of the fiber optics with erbium. And what it does is it allows the signals to be transmitted over longer distances with greater bandwidths. What happens is that they're placed periodically at spaced lengths, and the erbium-enhanced parts of the fiber actually function as laser amplifiers, which allows that distance to be increased. KGS coal research, KGSRE research. Starting back in July of 2014, we received some funding from the US DOE, and I want to note that this was stimulated and secured by our own Congressman Hal Rogers. Without his efforts, none of this would have ever taken place or is taking place today. What we were charged with was to assemble about 150 coal samples from the Central Appalachian and Illinois basins, which we then sent to a US DOE contractor for analysis. We did obtain some additional samples from Alabama, Mississippi, and Texas, because it quickly became apparent to the people at DOE that the people in Kentucky knew how and where to sample the materials to get to them, and they couldn't get that capability elsewhere. So I got to go back to my old haunts in Alabama. I'm an Auburn grad, so I spent quite a bit of time in Alabama. In addition to that, we took about 1,300 samples were collected from active mines, preparation plants, and coal-fired power plants. And these we analyzed internally at KGS in about 2.5 months. And it was a feat that I quite honestly, it was Herculean. We literally were analyzing material, prepping, analyzing around the clock, 24/7 for 2.5 months. It was quite a feat. In November of that year, final report was assembled, forwarded to DOE, and then ultimately presented to a congressional subcommittee in January of 2015. Based on the findings of that work, we then we applied for and were granted the research that we're doing today with US DOE funding. A little bit about how we analyze for REEs. We have sample collection, which would include mines, preparation, and power plants. All of that material has to be, it comes in, if it's from a preparation plant, we may be dealing with a ton of material. So all of that has to be accurately split and then sized. The size fraction that we use to test for these REs is about the consistency of baby powder. It's actually a little finer. It's what we call 325 mesh material, which means it has a top particle size of 45 microns. From there, what we have to then ash it. We have to put it into a porcelain crucible. We have to put it in a furnace at 500 degrees for about 6 to 7 hours, 5 to 6 hours, my bad. What that does is it burns off any of the remaining organic carbon in the sample, which we don't want. And then we take the material and we digest it. We use a combination of hydrofluoric, hydrochloric, and nitric acids. And this goes on to, they go into special vials, which are on a heating block here. And this one has about 45 samples that are digested. Okay. Ultimately, once the sample is digested, it is then analyzed with a machine we call the ICAP, which is inductively coupled argon plasma optical emission spectroscopy. Let's just call it ICAP. And in thinking about this, we go from literally days, weeks, months of sample collection to days of sample preparation to hours of sample action and digestion, and then finally minutes of actual analysis. So the analogy I drew is that it's kind of like having a colonoscopy. The preparation is far more detailed than the actual analysis. It's kind of anticlimactic. Okay, just to give you some indication of what we have found. One of the beds in eastern Kentucky that Jerry just talked about, the Firefly coal bed, we have found that it does have elevated amounts of these REEs plus yttrium plus Y. One of the reasons why we think it does have that is it has a very distinct parting. We call it a flint clay parting in the mining world. Sometimes it's called the jack rock. And it's been shown that this is the result of an ancient volcanic ashfall. And by the nature of it being volcanic in origin, that's probably one of the reasons why it has elevated REEs. Another thing that we found is that if you look at the numbers in blue, which are rock, versus the numbers in yellow, which are coal, the coal has higher concentrations of the REEs than do the rock. This is important because as we continually mine increasingly thinner beds, the actual mining equipment stays about the same, where they're cutting a minimum of about a 54 to 56 inch hole. So when they mine the coal, they're getting also some of the sheet rock and roof rock with it, which then is separated at the surface of the preparation plant. But you can see that some of our numbers here, the average of the fire clay here is a little over 1,000 ppm, and our rock average is under 300. Another reason why the fire clay coal bed, it seems to be a very good target bed is because it still has, even though it's been heavily mined, you just saw these from Jerry's talk, but if you look at the remaining resources in coal that's greater than 28 inches thick, we're still looking at about 40% of that. So it does have the potential of being mined into the future. And in thinking back to the real challenge for us now is to take that fire clay coal bed, which has about 1,000 combined REEs plus Y of 1,000 ppm, and ramping that up to 20,000 ppm. And the way that we're attempting to do that is through some rather sophisticated coal preparation. It's part of the research that's really out of my bailiwick, and so I'm not going to talk about it. But there is some indication that we may be successful in doing that. So with that, I'll just end it. It's a dirty business, but somebody has to do it, and it really is very, very interesting work. And in terms of a potential economic stimulus, we all know that anybody in the coal industry will tell you that times are just not good. So if there's a chance that we may be able to put some value-added if they can get value-added material from their mining operations in terms of REEs, that certainly would be a win-win in terms of coal production and also creating a new supply for rare earth elements for our nation. So with that, I thank you for your attention, and if there's time, I'll take questions.
Thank you, Cortland. I think we have time for one question with the caveat that whatever time we spend on questions takes away from your break. So, David.
Cortland, would you all be going back into manned out areas and targeting guile piles and anything like that?
Yes, that's one of the things that we're doing. One of the things about coal mining in Kentucky is that the very, very fine material, it is separated out in the coal material. It's separated out in the preparation plant, but then they don't keep it. It gets sluiced out to the waste area. And so we are looking at potential areas, especially with fire clay mining. How much material in these waste areas are we looking at as potential resources? Rather than something that was a problem, may turn out to be something that might be very, very helpful.
What about the coal ash after combustion? Does that have all the rare earth elements in it, or do you lose some?
It does. It does. The additional challenge with the coal ash from the power plants is that you're mainly looking at fused silicas. And so trying to extract the elements from the fused silica involves a lot of techniques that are environmentally challenging. A lot of hydrofluoric acid is used to break down the silica to release those elements. But it's something that we are looking at.
That's what you have graduate students for.
That's why they have me, Jim, not graduates.
Okay.